Hello, everyone. Today we are going to talk about strategy for integration. So far, we learned very different methods, and sometimes we'll need to apply one of them, sometimes two, sometimes even three methods in one integral. Let's kind of write down which methods do we know so far. Well, one of the biggest methods we are using always when we integrate is called substitution. What kind of substitution? It can be a simple substitution like u equals 2x, right? Or it can be more complicated substitution. U equals sine of x, right? Or tangent of x or cosine of x, right? More complicated substitution. It can be even more complicated substitution. X equals sine of theta. Do you see the difference? Here, new variable u is labeling the whole function of old variable x. Here, our old variable x is converted into new variable theta using the function. Can be not necessarily sine, but remember secant and tangent are working here. What else? What other substitution we can have? Uh, can be rationalizing substitution. Something like u equals square root of 4 minus x, for example. And even maybe it's a cubic root. So kind of all kinds of different substitutions, right? What other methods we also learned? We learned integration by parts. By parts. And some integrals cannot be calculated by any other method than integration by parts. What other methods? Partial decomposition. Remember about rational expressions. We remember about cases. It's 1, 2, 3, and even 4, right? So how do we kind of find out the method which we need to use against a certain integral? Usually, guys, you kind of do lots of homework and practice, and eventually you are going to build intuition on like which method to use. And also, there are some signs. For example, if you see a product, probably it's integration by parts. If you see a composition, maybe it's a substitution. And some, of course, some questions are not going to be that obvious. And usually you try a method, it doesn't work. Well, you can always try a different one, right? I'm going to place several different integrals on the board, give you some clues on the method we are going to use to integrate them. But I'm not going to calculate actually those integrals. I'm going to give them to you to calculate, okay? So I'm going to start with integral number 1, x tangent inverse of x in x. And I want you to identify, while I'm writing down integrals, identify the method you are going to use. Second one, 2x cubed plus 1 divided over square root of 4 minus x squared. I'm going to talk about each integral shortly, but I'm not going to calculate any of them. And there are not going to be too many of them. 3x plus 5 divided over x plus 1 squared. Yes, just 4 integrals. Let's just say a few words about each. And I think then maybe on Wednesday, when we have our class, we can kind of calculate them. So the first one looks like a product of inverse function and x. Remember, such products are always supposed to warn you that this is probably integration by parts. Remember, we had x by ln multiplied or x by exponential function. Very often here, by integrating by parts, you can probably eliminate either x or tangent inverse. We'll think which one is going to be easy to eliminate. Okay. Sometimes you can eliminate by differentiation. So I'm going to put here in parentheses by parts. Okay. Integral number 2. Well, you are going to look at denominator and recognize specific square root 4 minus x squared. And your intuition is probably tell you, well, probably we'll need a trig substitution here. Trig substitution can be sine, secant, or tangent. We are going to look at the form. It's like our binomial and decide which one we are going to use. Okay, how about number 3? Number 3 looks like it's a composition of exponential function and a square root. Maybe it's going to be very beneficial to use rationalizing substitution, or just kind of try to eliminate the square root from the power of exponent. To write down rationalized. Rationalizing substitution. And usually after you do rationalizing substitution, you are going to probably have a by parts after that. So lots of integrals are not solved just by one method. They solve by using two methods, sometimes three methods. And the last problem you probably recognize, okay, rational fraction, most likely cases 1, 2, and 3, right? What do we see over here, guys? I'm going to write down partial fractions. Partial decomposition, right? And we are going to pay attention to this 2, right? 2 means that the factor is repeat. And I think probably that's going to be enough for strategies. And we are going to solve all these problems in class. But right now, let's talk about um, all other integrals which are left, right? Well, we learned some methods. So basically, these are all the methods we use in calculus to find integrals. There are some more tricks, but not that many. So these are basic methods. But can we use these methods to integrate everything? So just take any function. For example, take a function e to the power of x squared, kind of fit the method into it, for example, substitution or something, and calculate. Actually, guys, no. Not all elementary functions can be integrated into elementary function. So antiderivative is going to exist for this one, but it's not going to be elementary function. Let's talk what is elementary function. Elementary function, it's going to be any of the functions we learned in this class so far. So it can be a power function, like to power function, like x to the power of n, for example. Can be a polynomial. Polynomial is going to be a bunch of power functions with coefficients, right? Can be exponential function, something a to the power of x, for example, or e to the power of x. Or it can be logarithmic function, or some like logarithmic function with base e, right? It can be trigonometric function, or it can be its inverse, right? Trigonometric function like sine or inverse, like arc sine of x. Or it can be hyperbolic function. Something like cosine hyperbolic of x, right? Or its inverse, cosine hyperbolic inverse of x, right? What else it can be? Also, we can combine all these functions using addition, subtraction, multiplication, division, composition. This way we can obtain lots of different functions. They are called elementary functions. Um, so actually not all functions can be integrated and give us the answer as elementary function. It does not mean that integral does not exist, but we cannot express integral as a formula. So there is no formula, for example, here, like e to the power of something multiplied by something and multiplied by something or divided by something. There is no formula for integral like this, but you still can find the integral because remember, integral is special definite integrals area under the curve. And the derivative, it's a function you differentiate and get expression from under the integral. It's just like, do know for sure that there is no function which is producing derivative e to the power of x squared. You cannot create it. But you can make it, for example, numerically calculated, such a function, define it numerically. I'm going to list over here the integrals for which we don't have the final formula. And you are going to be surprised how many of them and how simple they are. Well, first, e to the power of x squared dx. Second, e to the power of x divided over x. A very simple expression with exponential function, and you cannot find actual formula for this integral. Also, sine of x squared. Well, of course, can be cosine of x squared or tangent of x squared. It's a similar type with exponential. What else? X cubed plus 1. Just take our standard square plus 1 and make it into cube, and you cannot find the formula for it anymore. Something super simple about ln. You won't believe me that this one, you cannot integrate it or find the formula for it. Or for this one, cosine e to the power of x. There is no function you differentiate and get cosine e to the power of x. Or going to do one more sine of x over x. But you're supposed to understand that where I'm writing down sine, it can be easily cosine or tangent or secant. And all of them are going to have no formula when you integrate. Well, it's not bad. We will learn in section 7.7 how to find these integrals numerically or define them numerically. But for now, if you see them, don't waste your time on trying to use any of the methods. Just look at them for a while and try to keep it in mind, like which ones are like waste of time when you do the integration. So that's all about 7.5, where we had strategies. We are going to move to 7.6. So guys, in the next section, we are going to talk about integration using tables and computers. And when I'm saying computers, I mean uh, computerized systems, algebra, or, like Mathematica, something like Mathematica or MATLAB or Maple, where you actually can integrate like you do it in class. Computer can do the integral for you. Um, so Well, before people invented computers, they were using tables. Tables are like general formulas. For example, somebody calculated a certain integral, and then instead of specific numbers over there, placed general constants and kind of give that formula. Next time you see the integral, you can kind of just use the formula instead of doing all the steps. For example, trigonometric substitution. Uh, I'm going to consider an example of using the table. And we do have a moderate table of 120 integrals, I think, in the reference pages of our book. And there are bigger tables, which are kind of books by themselves. And there are even bigger tables, which are even bigger books. But it's going to be enough for us to have that little table of integrals in reference pages, because normally, guys, in class, I'm going to always assign you integrals which you are supposed to calculate by yourself. That you're supposed to know that there's opportunities of getting integral calculated by somebody and using ready formats. Let me show you an example of how it can happen. For example, a little bit bigger. For example, I'm going to consider integral x squared dx divided over square root of 5 minus 4x squared. If you look at this integral, you probably can guess that trigonometric substitution is going to solve it, right? Because we have like a number minus square. Maybe your substitution is going to be 4x squared over 5 equals what? Sine of theta, right? And this substitution is going to solve this integral, but you will need to do lots of steps because after you apply the substitution, your numerator is going to be modified too, and then you will need to calculate trigonometric integral. And somebody did all this work for us. Imagine that you look in the reference pages and you find a similar integral, which is going to look like this. Kind of generalized form of our integral. If you compare it, you see, yeah, x squared dx, u squared du. Here, a square for kind of some arbitrary number, 5, and here u square. And if you compare with our integral, a little kind of difference here, we have 4x squared. So we can probably do some extra substitution to adjust our formula, our integral to the table integral, and then use the formula. So somebody calculated actually this integral, and he found that answer is negative u over 2 square root of a square minus u square plus a square over 2 sine inverse of u over a plus a constant. So somebody already did all the substitution, managed all these numbers everywhere, the constants, minuses, and he got the answer. And if you kind of just plainly take this integral, you can, right now, you can calculate it easily. But let's kind of see how the formula is going to work. So we need to bring our integral to the shape of the table. So we don't want to have a 4x squared here. We want to have one variable here. So I'm going to set up u squared equals 4x squared, from where u equals 2x, right? And du is going to be 2dx. Now we are ready to rewrite our integral in a shape more similar to the table. So instead of x squared, we are going to write down u over 2. Why u over 2? If you solve this equation for x, it's going to be x equals u over 2. So u over 2 squared. Instead of dx, you are going to have du over 2. If you solve this for dx, it's going to be du over 2. In denominator, we're still going to get 5 minus, and now because 4x is u squared, we are just going to have u squared. Now, my formula is matching much better the table formula, right? We just need to simplify a little bit and get rid of these 2's. We have 2 and like 4 here, right? So we're going to have 1 over a integral of u squared du over square root of 5 minus u squared, which is exactly the formula we have over here, right? So we are just going to use the answer. Guys, I'm going to continue writing down below. So after here, I'm going to put equal sign and write down below. So it's 1 over 8, then minus u over 2. My a here is, this is a square, so my a here is a square root of 5. Be careful watching the constants. Instead of a, I should write down 5 minus u squared, and then plus 5 over 2 sine inverse u over square root of 5 plus a constant, right? On the next step, I'll need to go back to x, actually, just reverse substitution. So u equals 2x. So I'm going to write down 1 over 8 minus 2x over 2 square root of 5 minus 4x squared, squaring it, plus 5 over 2 sine inverse of 2x over square root of 5 plus a constant. Well, after this point, we can simplify it a little bit more, but generally speaking, we are almost done. So we just need to maybe cancel this 2 and this 2, and maybe multiply this 8 by the rest of the formula. Otherwise, that's going to be our answer. You see, formulas are very easy to use. But in this class, we are learning how to create formulas like this, right? I'm going to give you one problem to do for self-work. And here again, I'm asking you to use table of integrals, okay? So find the integral e to the power of 2x arc tangent e to the power of x dx. So here you probably will need to do a substitution, clue substitution, e to the power of x. I'm going to put maybe. It doesn't look very nice. So here I want you to go to reference pages. Find the formula in reference pages. And use it. Okay, after you do substitution. And I think that's going to be it. We're not going to use tables a lot, but in your future life, when you are not in class or not doing a test or quiz, you can always use the tables. And lots of computer systems, like Mathematica, can actually even show you how to obtain the final answer doing steps. So you are always welcome to use technology when I'm not specifically checking your knowledge about like how we obtain that. Okay. And I think that's all about section 7.6. Very short section. That's why I'm combining it together with 7.5. Okay. Okay, that's all. And we are going to discuss the integrals from 7.5, which was about like techniques of integration or strategy. And this one, integral from the table in class, right? Okay. See you in class.